Okay, I'll wait maybe like a minute. Only a few guys are here. I guess we can start. Okay, so today we go into a new chapter, the second chapter of this course. Okay, and that is the first of the device or the machine, the electrical machine that we are going to study. And this is called transformers. Okay. So what does it do? It is a device or electrical machine that changes AC, electrical power at one frequency, and voltage level to an AC power, AC electrical power at the same frequency and another voltage level. Okay. Should be at another voltage level. There's a typo. Okay. So basically, you're changing AC electrical at one level of voltage to another levels of voltage, both at the same frequency. Okay, here, so you convert AC voltage levels to another of the same frequency. That's kind of like in a nutshell. Okay. So, and again, remember, this is based on Faraday's law. So it means that transformer only works in AC voltage. Don't get confused about DC transformer. There's no technical term. DC transfer does not exist. Okay. When we talk about transformer, by default, that is AC voltage system, always. Okay. There are devices that do perform DC voltage level variation, step up or step down. But remember, we do not call them transformer. Okay. Whenever you heard the word term or the word transformers, it is AC equipment or device. Always, always. Okay. And remember that the reason that it's part of the electric machine family is that they don't, you notice that doesn't involve anything in terms of mechanical, but again, they do rely on the same principle as the other two types, generators and motor, where magnetic field is our medium of conversion. Okay, so basically, you have a transformer, and from now on, I'm going to write TX for transformers. Okay, it's kind of like my short handwriting. The word is way too long to write. So basically, what you're doing is that you have a voltage here, AC. You want a output voltage there. Okay, so here you can either step up or step down. Okay, again, this is AC. Okay, inside, the main idea is magnetic field. You need that. You can do that. Okay, now don't get confused. Why do I emphasize on this? You can have this device. I can have a device. Okay, that can also do the same job. Meaning, I have, let's say, I have 220 volt AC, 50 hertz. I can also generate, let's say, 110 volt AC, 50 hertz. But here, no magnetic field. Okay, I can use some other means to convert Okay, if this is the case, this is not a transformer. Okay, if there's no magnetic field involved, it is not a transformer. Okay, you have to remember that. Whenever we mention about the term transformer, the word transformer, you need a magnetic field to do the conversion. Okay, and we talk about that in the first chapter. We have 3 types of electrical machine. All of them are rely on the same principles of the magnetic field as our medium. Okay, that's why this belongs to one of the 3. Okay, now once we understand our definition, it is a pretty simple concept actually. Okay, I never actually find out who was like the first inventor. If my guess is correct, should be like Tesla. He's one of the guy. Anyway, okay. But the construction is very simple. You guys can do it if you have the materials and the proper lab. I'm not sure if you in your class you guys still have mini projects in the lab or not. But we used to have you guys done a mini project in a lab, making a transformer. Okay, but pretty simple. It consists of 2 or more coils or windings. Okay, windings connected to the source, AC source. We call that primary winding, PRI for short. This is the input winding. Windings connected to the load. Secondary winding. This is called output or SEC dot winding. Okay. Sometimes you have 3, meaning you have 2 sets of winding on the output, but that's not really common. But you can do that. You just call it tertiary winding or third winding. So basically, in a simple construction, we've seen you guys seen this before in chapter 1. I have ferromagnetic core. Remember the square donut? This is ferromagnetic core. What you have is 1 windings. This is connecting to the source. So this is primary winding. You have a secondary winding connected to the load. If you have a load, which is usually the case, this is secondary winding. That's it. Pretty simple construction, and it does work. Okay, pretty accurately. Okay, when we learn about the relationship later. So this is a very simple concept, simple idea, and notice that there's no physical connection between the 2. We'll talk about that later. So the ways we get power or energy from this side go to the load, you need magnetic field, which is a magnetic flux linking between the 2. See, that's the only thing that's going to be relating these 2 coils. Both of these coils are not physically connected. They are isolated, separated. Okay, and there's some benefits of that. We'll talk about that later. Okay, so this is the means of transfer for the energy or power. Okay. We use it every day, you and me, you and I. Okay, every day. I'm assuming 24 hours, 7 days a week. 365 most of the time if we have electrical power. Unless you travel or you go to like outdoor or the park, but highly likely that we use it almost 24 hours a day indirectly. Okay, so the question is that why is it part of our lives? Why is it so important? So this is one of the questions that your textbook was asking, which is you need to know. Okay, why transformers are important to your modern life. Okay, and I said this mini semester now. You should watch. It's part of it's a biography, I think, kind of. But there's a movie just coming out few years. I don't remember what year back. They called the current war. Okay, so that's kind of like a story between Edison's, Edison's, right? Thomas Alva Edison's and Nikola Tesla. The fight between the current war means AC current, DC current. There's a war going on back in, I don't remember the year anymore. Okay, if you have the time, you can watch that. That's a pretty, it's a drama movie, but it tells you a little bit about, what's the reason behind, the voltage system that we are using today. If you look around you, in the entire world, we are using AC voltage system mainly, okay, in terms of generation, transmission, and distribution, okay. But some of you is gonna say, hey, but your phone is DC, electric cars DC, your tablets is DC, your computers DC, but those are like a secondary source, meaning that you want to use your phone, you need to charge your battery. How does that work? You need a single phase AC, right? That's how you charge your phone every night or during the daytime. Okay, so you still need AC to DC conversion. Okay, but we mainly, producing or generating AC, three-phase in particular. Okay, and there's a reason behind that. That's like the beginning. Why there is always an argument, which system is better, AC versus DC. Okay, up until today, present day, and maybe I don't know, a few years or decades from now, AC would still be the dominant system in the world. Okay, but we don't know. For 100 years from now, maybe AC doesn't really exist anymore. Okay, but in the beginning, I guess all of you or some of you should know Tesla, Nikola Tesla, and I'm assuming most of you should know Edison, right? Edison is famous for the light bulb. He's one of the inventor of the electric light bulb. Okay, but Edison likes DC. He's like, what's the term in English? Proponent of DC voltage system. Okay. Tesla, on the other hand, Tesla said, hey, I like AC. He liked AC voltage system. Okay. So there's a fight between the two. I think at one time, Tesla used to work for Edison, and then he just kind of like pushed the idea of doing this would be better, but Edison never really liked that idea. He just liked his idea because he's like, he invented lots of things for us today. You watch that movie, there are many things that's, you never thought that he invented, like I think video, camera, or I don't remember the movie play or something like that. He's one of the first guys who invented that too. Like the, how you say it, record player, like your MP. Well, not nowadays. You guys don't use MP3 anymore, right? It's gonna be like what's your generation? Spotify, Apple Music, right? You listen to your music through the internet now. But let's say 10 years before that, there's MP3 player, like the, what's the name? iPod. Yeah, there's an iPod, and before the iPod, there's a what do you call it? CD player. I'm talking about the history of music, recording stuff, device. Okay, before CD player, there's a Walkman, cassette tape. Okay, and then prior to that, what do you call it? A turntable, vinyl collection. Okay, so he's one of the guys who can put music into a portable device. You can think of him, he's like the father of portable music, sort of. Okay, but anyhow, he likes DC. He's got a company. He's like one of the founder of the company that some of you might have heard today, General Electric, GE, the company that, you know, builds like aircraft engine, in healthcare, in electrical machines in general. Okay, so he used to be one of the big company, GE, General Electric. He's like one of the inventor of that. Okay, but they change owners over time, but he's the guy. And then came along Tesla. Okay, Tesla invented like a dynamo, which is the prototype of a generator, AC, including AC motors. Okay, now Edison start the light bulb because he has this electric company using DC voltage. He want to sell his, you know, all the tools and this energy and the, you know, the devices. Okay, he want to light the New York City streets. I think that's the story goes. Okay, so he built this DC voltage system in New York City. But the problem with that system, with this system, remember, you guys have to remember, this is like a rule in electrical engineering that you have to remember, is that electrical load, you know, your load, electrical load, okay, they use power, uses power, okay, electrical power. By default, this is electrical load, this is electrical power. And for you guys, you should know this. Electrical power in terms of equation, what is that? P equals to the voltage times current. I'm using your basic definition here. Voltage times current is power. This is not really true. It's apparent power, but that's okay. Just forget about that. Let's use this one. Easy to understand. Okay. Now, we do not, I repeat, we do not use either the voltage or the current. We use the product of both. We use power. Your load, I mean, the load uses power. It consumes power. In this case, real power, active power, okay, average power, they all mean the same thing, okay. If you study circuit, I think there's different types of power, 3 of them, okay, but ours are real power. These are real, you can measure it. The most common concept that you guys would understand is we can measure it in terms of heat, okay, in terms of the I square R losses, which turns into heat. So these are real. You can actually feel it. Human can, how do you term it? Not see, but you know, can actually kind of like feel it. Okay. Why do I tell you about this? There's Q. Remember Q? These are reactive power, imaginary. You can't really see or feel this. Okay. So, but these are real. Okay. We humans uses power, energy in a sense. We consume like food, right? Vegetable, fruit, meat, whatever it is that you consume would give us energy, which translates into power. Okay, remember power through time is energy. Same meaning. We don't really use Q. Now, so that means, now back to our story. That means when you have power, you use this. You don't use either V or I, you use the product of both, okay? Now, as you notice that if we're using your device, equipment, electrical equipment, notice that if you're in Thailand, all the ratings would be 220 volt AC, right? Assume 50 hertz. So that means your load, or your whatever it is that you're using, electrical fan, your refrigerator, your phone charger, would be fixing the voltage. You want the device or the equipment that you are using expect to see 220 volt source. Okay, so that means your voltage is fixed. Okay, that means if I have, so this is how Edison's working. Assume that he has a power station. It's supposed to be a source. Okay, he generates an amount of power. Okay, I'll give you an easy number that we can calculate. Imagine this is 1,000 watt, arbitrary 1,000, or if you say 1,000 megawatt, whatever it is. Okay, his power generating system would supply power to each home. Let's say Okay, let's say I have one home. Okay, again, this home, all the equipment in this home needs, for simplicity's sake, let's say 200 volt. Okay, remember this is DC. Okay, that means assume this whole house consumes 10 watt. Okay, so that translates to a current of this number one house to be what? What is the current? Do you know? So you just, the current is the power divided by 200. Well, let's make this 100, easier to calculate. Okay, so the current would be 0.5 amp. Okay, so that's good. Now, turns out that there's not one home, there's a second home connecting to that. Again, all the loads in this home would still consume 200 watt, not consume, uses 200 volts, sorry. Let's say this house is identical to the first one, it will consume also 100 watt. This current would also be 0.5 amp. Okay, I2. Now imagine what is the maximum number of homes that I can use. 10 houses assume identical, right? 200 volt, 100 watt. Okay, so we'll get the amount of current. The total current would be, what, 5 amps. Now, if I want to supply more, okay, I can increase my power on the source. If I do that, now notice that what we are doing here is that your voltage in the first column on your left is fixed, while your current, okay, let's say I conclude the total, V total would be still 200 volt. But now your I total in this case, it's 0.5 amps times, I can have 10, right? 10, 5 amp, okay, at 1,000 watt. I have, if I want to sell more power to additional home, let's say I step up my power generation to 200 watt. I can sell another 10 homes, right? Now, the voltage doesn't change. It will always be 200 volt, but your current is going to be what? 10 amps now. Now, you say, hey, that's okay. It's from 5 amp to 10 amp, linear, right? I can increase this to, I don't know, let's say 10,000 watt. My current can increase to what? 50 amps. Okay, notice that the more I increase my power, the more current is going to go up. Voltage doesn't change. Okay, what's the problem with the current? These current for each home would generate, let me go to scrap paper. The current I that you have will give you power losses in terms of I square R. So the more number of home I increase, the more current I would end up increasing, the more power losses would go up, in the power twos of that. Okay, if you have a large enough current, your loss would be so huge that this would not work. Okay, and the reason, now you cannot say, hey, let's not do that then. Let's say your power remains the same. Remember, we use power. It can either change voltage or current. Then you can say, hey, why don't we keep the current the same? Try to make it minimum, but increase the voltage instead. Now, that is where your DC voltage system has problem. To step up the voltage, to keep it up, remember, I'm explaining this in the loop. Remember, power, it's either a function of either a voltage or current. Okay, I want power to go up. I can fix this, increase this. This is causing more losses. Okay, I square R. If I don't do that, instead, I say, hey, power is a function of voltage and the current. I want power to go up. I fix this. This is fixed. I fix the current instead. I want this to go up. Assume you can do that. This is good, better, right? Your power losses doesn't change. Okay. But to do that in a DC voltage system, back during Edison's day, even today, technology is still not cheap, expensive actually. Okay. You need a lot of, I'm not sure during Edison's day that would work or not, but he cannot do that. Okay. So come along Tesla. Tesla said, hey, instead so during Edison's day, how does he do? So he instead of doing this, he has to build his power station in New York City every 10, I don't remember the number, every 10 city blocks or so to match up with the demand. Okay, which is not really, what do you term it? Economy of scale, because there's a huge cost doing that. Back to Tesla. Tesla said, hey, I have a technology, I have a theory that instead of doing this, I can increase the voltage in a simple manner. Okay, that's where your transformer concept comes in. Tesla said, I can have this 2 coils, it's my coil. Okay, connection between the two, I have 1 voltage here, I can increase this to a higher value without sacrificing the current value. See, so that's why AC powers are a winner today. Okay, because imagine in today's city, I don't know how many homes we have, you want lots of power, and in order to get that power, and remember, we do not generate our power close to the city, we generate power close to our source. Used to be in Thailand, most of our power comes from hydroelectric dam or coal mine, the coal. So we have our power station near the electric dam or the coal mine in northern. Now we generate our power via natural gas. So our power plants are located close to the port or close to the country that sells us natural gas. Okay, like the eastern side of Thailand, for example. And because we generate power over there, we have to transmit it over here. Okay. Now, let's say I generate 1 megawatts of power. Okay. Now I want to see, you get to see an example later. Okay. Now I want to, let's say I'm 100 kilometers away. This is your Bangkok. I want to get this power, 1 megawatt, to Bangkok. Okay. If I, have this at 200 volt, let's make it 2 megawatt, that's easier. If I use 200 volt to, transmit this 2 megawatt to Bangkok, what is the amount of current in a transmission line? I'm doing this very simple. So your current is 200, 2 megawatt, 60, right? Divided by 200 volt. 1,000,000. So you get what? 100 kiloamp. See how that works? You need 100 kiloampere going through these transmission line. Assume your transmission line has a resistance of 0.1 ohm. Pretty low. Okay. What is the power losses? Your losses in the transmission line would be I square R, 100K square times 0.01, I'm sorry, 0.1. How much is that? This is 10 to the, how many? 5th, right? 10 to the 10th times 10 to the negative 1, 10 to the 9th. What? How big is that? The loss is a lot greater than what you generate. You see, you generate 2 megawatt. This is what? 10 to the 9, 1,000 megawatt. So this is not possible. See, so the only way that you can transmit this, I'm using only 2 megawatt, which is not really true. The number would be like, I don't remember the number, gigawatts, I think, many gigawatts. So here, if you look at these numbers, this is not possible. Even at 2 megawatt, I need 100K amp to do that. So instead of doing that, I do the other way around. I increase the voltage. I will maintain the current at a very small value. Let's say I increase it to 200 kilovolt. See, if I do that, this is going to give me a current value of, same thing, 2,000 divided by 200K, 20 amp. See, look at my losses now. 400 times 0.1, 40 watts. You see the differences here. Now, the first system, not feasible because I generate 2 megawatt. My losses is 10 to the 9, which is what? 1,000 megawatt. Not feasible. I look at system 2, I do the same thing. I'm trying to transmit 2 megawatts of power, but now I have to increase my voltage to 200 kilovolt. I get my current down from this, 100K to 20 amp. You have to check my calculation, but I think that's about it. My losses drops from this huge amount, unimaginable amount, to 40 amps, 40 watts. So this is feasible. And that's how we've been doing our, transmission line today. See? Now, why doesn't this system works in DC? In DC voltage, you can, but not in a convenient way. You cannot step up the voltage easily. In AC, you can step up what you generate to 200 kilovolt in a simple manner. So this is the reason why transformers are very important in your daily life. Okay, I'm trying to explain this. Okay, you want a more description, you might want to read in textbook, but here in a more written form is that power, which is the average power, or sometimes called active power, real power. This is the one that the electrical load used. It's a product between voltage and current. Okay, and your current depends on the load demand. Okay, the more demand, the more the current that we want. So again, we use power, so if there's more demand, P is going to go up. So to keep, loss minimum, the loss at minimum while P is increasing, you can either increase the voltage or the current. But if you increase in DC voltage, changing the voltage is difficult, especially during Edison's era. Okay, difficult and expensive. Even in today, it's still very expensive to do. So if you increase the current, so that means in DC you cannot change the voltage, so you must increase the current. But if you do increase the current, the losses in terms of I square losses, we go up dramatically, not linear. Okay, and that's going to make the system not feasible. So therefore, to increase the power, increase the voltage is preferred. Therefore, and this again, put that in. Therefore. To increase the power, increase of voltage is preferred. And this is done by transformer in AC voltage system only. Okay, only. If a transformer steps up the voltage level for transmission over long distances, the transmission line losses are relatively small. I showed you the numerical example moments ago, right? So now you understand. Okay. Modern power system is generated at voltages of 12 kilovolts to 25. This is at the generator side, but this is not high enough to transmit. what you must do is that you need transformer to step up the voltage to about 100 kV to 230 kV. See, so the numbers that I just, 9,000 actually, for transmission over long distances. If we do that, your current is going to be minimized, and that's going to reduce your losses. See, so this is why transformers are very important. Okay, you need to step up the voltage in order to deliver your power. Okay, if you don't, your losses in the transmission line would be huge, so huge that you don't get any power on the user end. Okay. So that's the reason why we do need transformer today. If you notice that, you know, like well, at Bang Na, it's not really, it's all in a building, okay? But if you go, you know, if you live at, you know, Bang Na campus, or you live in a city, if you notice that some of the transformers are installed on electrical pole, you know, there are many shapes and form. The one that next to my house is like a barrel shape, kind of like a big capacitor, sort of like a barrel. And what you're going to see like a ceramics insulator coming out. Okay, so those are next to my home, and then some of them that you can see kind of like a box shape, metal box, pretty huge. And again, you see ceramics coming out. So these are transformers that we talk about. Okay, so our main focus in this class is power transformers. Huge, big size that you can actually see. You would travel within Bangkok or, you know, outside. Okay, just, you know, see what it looks like. Okay. Okay, so that's the reason why we do need transformer. Without them, you know, we don't get electrical power to your home. Okay, unless you are self-generation, but you know, in general, you cannot do that. Okay. Once we understand the concept of, you know, electrical load uses power, and the ways to increase the power based on load demand is to increase the voltage, not the current. We will try to minimize the current. Okay. All right. For power transformer, okay, we have constructions and type. So before we move on, let's look at a basic model of symbols, okay, and the notation in a transformer. Okay, mentioned earlier that your transformers are built using a core, ferromagnetic core. Okay, and the ways that we transfer the energy between the primary and secondary is by means of magnetic induction. Okay, no physical connection. All right, so in this case, I'm showing you a basic diagram of what we call a core form transformer. Okay, basically, it's very much similar to the basic model I draw, kind of like this, but these are just for your easy understanding. A more practical construction will something look like this. This is to minimize the losses along the core. Okay, but basically showing you here, there are two sets of winding, red winding. Notice that we have connected to the source voltage, we sub P as a function of time, showing you this is AC. That coil has the current flowing in, I sub P as a function of time again. And then these are the same coil because they are linking by this, you know, windings. So this red is called primary windings. It has N sub P number of turns. So N sub P is the number of turns of the primary winding, which is connecting to the source. The black windings, polarity the same, plus and minus Vs of T, but this time your current flows out, ready to the load, I sub S as a function of time. This black winding has a turn of N sub S. So N sub S is the number of turns of the secondary winding, which is connected to the load. Okay, so when we say primary, automatically means input connecting to the source. Secondary winding automatically means output connecting to the load. These are what we call core form constructions. Okay, we can have a more practical in terms of saving the losses and a better performance transformer. This is what we call a shell form construction. Okay, they do the same job. You have the blue ink, primary winding, wrapped in the center leg. Notice that this is a three-legged cord that we kind of like did practice on for the first chapter. And then the red windings, secondary, connected to your load. Okay. Between the core form and shell form, core type and shell type, sometimes they are called, the second one is a better in terms of performance transformer, because the second one is the leakage flux are reduced. Okay. Okay, this is due to lower leakage flux, because if there are leakage flux around these wires or windings, it will be trapped within the core. On the top one, if you have leakage flux, that's going to go to waste, to the environment, to the air outside. Okay. But in terms of constructions, this is easier to make. This is more difficult. Okay, you need a more complicated tools to do. Okay, so there are trade-offs between the two. Okay, but they do the same thing. Two windings perform everything is the same in terms of theory. Okay. Now for power transfer, there are a given name and uses according to its purpose. Okay, this is just to give you an idea. The terminology in power system transformer. Okay. The first one, probably large, very large size transformer, especially in terms of capacity. This is what we call is unit transformer. Okay. So let me draw you what we call this a one-line diagram of power system. Okay. So I have a power plant. This is my generator, somewhere very far away from Bangkok. Let's say I generate, I don't know, 20 kV, very high voltage, but not high enough to transmit. Okay, one line only. So here, I will connect this generator to the power plant. Maybe this is a steam turbine generator, whatever it is, next to yours. Excuse me, primary source, hydroelectric dam, coal mine, whatever. You connect to a transformer. This is what we call a unit transformer. Usually they are located next to one another, next to the generator or close by within the same building. This is to step up. Okay, its job is to step up from generation, which is in the range of 12 kV to 25 kV. This number might change a little bit. Okay, usually in that range, in the tens of kV, not high. Okay, 34 maybe. That's it. What does it do? It steps up these, even though kV, 12 kV is pretty high, right? Or 25 kV is very high, but not high enough. You step it up to the transmission voltage level. This is usually above 100 kV, 110 or more. Okay, so in this case, let's assume I have 20K. I would step up to, let's say, 230 kV. I use a number that's more like a practical number. And then on this side, connect this to a transmission line. The one that you see, if you go outside of Bangkok, along the street, along the road, especially like in a highway, You have this big electrical pole, you know, with, you know, several wires hanging between the poles. Okay, the other transmission line. So it's pretty far away. Okay, so this is what unit transformer is about. I'm sorry, I'm doing this the wrong way. It should be one line diagram. I'm mixing, so it should be something like this. Generation, unit, 20 kV to 230 kV. And then this is transmission line. Okay. Then the second one, it used to be available to see, but you can, well, if you look around, this is called what we call substation transformer. Substation, it's a word in itself. It means, I think, I'm guessing here, I never really check it out. It's a substation of a generator station, okay, a sub of it. So these are usually like a field. You can kind of like Google and look at the pictures of it, but it's like a field that have fence, and you see this, you know, high voltage, you know, warning signs, and then you see apparatus, but it's usually like a pretty, how would you term it? You don't, there's no building really. Okay, all the electrical apparatus is, you know, outdoor, no roof, anything like that. Okay, so these are substations, so they are along your transmission line. Okay, and usually they are close to some major city. Okay, so that means I have a lot of power here. So we go to each substation. Let's say this whole power plant supplies power to Bangkok and vicinity, you know, like, you know, Samut Prakan, like Patum Thani, you know, whatever it is. So let's say I have like, you know, I'm giving you an easy example here, 4 substations. Each one belongs to each province, but, you know, usually it's a lot more than that. Okay, so these are what we call substation transformer. Okay, its job is to step down from the large transmission voltage level ready to be distributed, so to distribution level. Okay, so this is 230 kV. You step it down to, let's say in this case, in the tens of kV, let's say 23 kV. Okay, or sometimes down to 2.3, but still in the range of kilovolts. Okay, so this is substation. Sometimes you can see this. Unit transformer, I see one, it's very rare to see, about the size of your classroom, the size of 2 container. You know, the chip container, right? About 2 of them, you know, stacked, well, not stacking, next to each other. Very, very big. Sometimes you can see, well, you can't. You just see the building. Substation, if it's within like the city of Bangkok, is usually installed in a building where there's no window, you know, and you can see the MMeca sign that the property belongs, the building belongs to the MMeca. You might want to, well, you got to know where to look anyway. Okay. Anyway, then from substation, then I'm gonna expand this even more. I'm ready to distribute. So now you go into each, you know, villages, you know, like the one you come to Dang Nai campus, you know, lots of, you know, homes. Then you have another stepping down. Okay, so these are what we call distribution now. Distribution transformer. Distribution. Okay, so what does it do? It steps down one more time from distribution levels in terms of kilovolt down to the actual voltage level. So in Thailand, it's 220 volt. So these transformers are the one that you can see on the electrical pole, you know, somewhere around, maybe on the building. We go to like a shopping mall, go to the restroom in a shopping mall. There are rooms that have these apparatus. Okay, so this is where where they're located. Okay, So now it goes to, your homes. See these, so these are the names. You should kind of like know what they means. Okay. Okay. Now, the fourth one. So we have unit, substation, distribution, the one that you see the most here. You have another one, what we call special transformer. They are two subtypes. The first one is what we call potential transformer. The second one is current transformer. These are special purpose transformer used for measurements. So we are using it to measure either high voltage or high current. Okay. Imagine you stepping up to 230 kilovolt. That's a huge number. How do I know it's 230K? You cannot use your ohm meter to measure that. No. At 230K, if you get close to it, you don't have to touch it. Maybe like a meter next to it, that would probably cause electrical shock to you already. So this is a very dangerous high voltage level. Okay. So, the voltage is going to see you like a conductor, because our human body contains fluid, right? Your blood, your water. So it's going to look, whoa, you're like a conductor. So the electron's going to jump. You can arc over across the air. So 230 is very, very dangerous voltage level. So how do you measure this much voltage level? You use what we call a potential transformer. Okay. They work the same way. You have a relationship between the windings, and you step up to measure it. The second one is what we call current transformer. This is used to measure high current transformer, high current equipment. The idea is to use your magnetic induction. If you are taking lab number 1 in machine, you might want to look at the ammeter that you have in the lab. On the back, you're going to see something that looks like this. Kind of like that, and then kind of like a circle in the center. Okay, and there's going to be terminals coming out. Okay, now the idea of a current transformer is that this is going to go to your meter, your dial, and then you want to measure the current in these windings. Usually there's a winding wrapping around. Okay, so the idea is that if there's a current in this winding, you want to measure how much current. This winding current would generate a flux in this coil. That flux would induce another windings connecting here on the top, and it will show the readings on the meters. So these are the concept of current transformer. But for large current, some of you might have seen a current clamp. Okay, it's like a clamp. I don't know what's the term in English, like a piler. I'm trying to draw. You can Google that too. I'm like this. I'm trying to do this. Like a clamp. Okay, I like that. And there's like handle. Okay. This one is going to be connected to a meter again. But then you clamp this across a cable that carries a current. Do the same thing when you have a current carrying conductor. You will induce a flux around it. This flux would give you the reading on the meter. Okay, so this is current transformer, special purpose. Okay, enough about descriptions. Now let's go into your, equations. Okay, now first we're going to look at ideal transformer. Okay. Ideal transformer are, lossless device, meaning you have 100% efficiency, resulting in the ratio output and input power are the same. Okay, so I'm just going to give you a basic diagram here. This is not a practical construction, but just a simple shell type. I'm sorry, core type construction. We have windings, the black, primary, again connected to phase voltage. V sub P supplies the phase, primary voltage, give you primary current into the primary coil with N sub P turn. This coil will generate a flux in the blue here, linking to the second coil, which is secondary in the red here, has NS turns, and the voltage same VS, where the current's going out, ready for the load, I sub S. Okay, and there I have two dots. This is not a typo. You got to make sure that there's a dot, black dot there. There's a red dot there next to the winding. I'll explain to you guys later. So these are the ideal transformer concept. Okay, so both windings of a transformer are not physically connected. I mentioned that. They are what we call is magnetically coupled. Okay, if they are not connected, we have what we call is electrical isolation. Okay, why is electrical isolation? It's a good thing. Okay, there's positive and negative points to that. The positive point is that whatever happens on one side, usually on the load side, if I connect this to a load and something happened, an accident happened, on the secondary side, there's a short circuit here. When there's a short circuit here, notice that if my secondary is shorted, I have no voltage. Okay, assume I have initial current values there. And we get some amount of flux. Nothing's going to happen on the primary side because they are not physically connected. No conduction between the two. The only link between them is flux, but flux doesn't really change according to the shorted current. Okay, so this is what's so good about electrical isolation, and they are transferred using magnetic field, the power. So energy is transferred via magnetic induction. Okay, we call this, appropriate term for this chapter is transformation. Okay, now what's so simple about transformer is that you can, design it in a simple manner in terms of the voltage ratio, okay, which is written here. The voltage ratio between primary VP divided by VS is equal to the ratio of the number of turns of that associated windings. So VP over VS is N sub P over N sub S. As simple as that. This whole thing has a symbol of A, or a regular A. Its name is what we call a turns ratio. Okay. And A can have any number except 0. So it can be a negative, has to be above 0. So it can be greater or smaller than 1, but never 0. Okay. So that makes our lives easier if I have a transformer. I'm connecting to 220 volt source, 50 hertz. I want the output to be higher. I want 440 volt. If I have this 100 turns, I just basically do this is 200 turns. I would get 440. You see the range shift. VP over VS is N sub P over N sub S. Okay, so if the ratio is, 1 to 2, it has to be 1 to 2. See? So, and this applies to real transformer, which we'll explain later, but this is true for ideal. Okay, so no matter how much voltage you want, either step up or step down on the secondary side, you just change the number of turns of the secondary, or you just change the ratio between the two. You see how easy that is. Okay, you don't even need like a calculator to do the calculations for the winding number of turns. Okay, so this is the voltage ratio. And again, because we're dealing this with the ideal transformer, so everything is the same, no loss. So S in, parent power on the input has to equal to that of the output. If the parent power is the same, so VP IP, voltage times current, gives you a parent power on the primary, which is the input side, must equals to that of the secondary, which is VSIS. Okay. And if you do this relationship, you know VP over VS, you can find the current ratio. IP over S is 1 over A, which is N sub S over N sub P, using this relationship. See? So you look at this carefully. The voltage ratio is VP over VS, N sub P over N sub S equals to IS over IP. Just switch for the current. See? And this is a letter A, turns ratio. See? So it is a very simple concept. Okay, you see how smart Tesla is? You know, he just know, hey, if I have this, I can actually do this in a simple manner, stepping up the voltage. And notice that no electronics, no transistor, no IC, no capacitor needed. See, these are the basic equipment, device, simple concept, and they do work. Okay. Circuit symbol or transformer is two inductance in parallel vertically, and sometimes you see two vertical lines, which represent the iron core transformer. Most of the time it's neglected, omitted. Okay, and again VP, IP, current going in, dot, dot, just like that basic diagram. This is a circuit symbol. And then VSIS, IS going out. A more common would be like on the one on the right here, but they're the same. Okay. Now, remember we're dealing with AC. So we have phasor, you know, phase voltage, phasor voltage, voltage phasor, current phasor. So would the turns ratio affect? Okay, it turns out that turns ratio in terms of phase quantity. So we have VP bar here, phasor, divided by VS is equal to A. IP over IS is 1 over A. So similar relationship. Now, one more thing that you have to note. Note that turns ratio, your letter A of ideal transformer, does not affect the phase angle of the phasors. Meaning what? If I have my primary voltage of 10 volt, 10 degrees, okay, my turns ratio is 2, then I can use this relationship to find out my secondary phasor voltage, which becomes 5, right? In this case, VS is VP by A, so 10 by 2 is 5. While your angle remains the same at 10 degrees. So your turns ratio doesn't involve changing the angle of the phasor. Whatever angle that you have originally would be the same. It only here, only magnitude are affected. That's it. Okay, don't divide the angle by the turns ratio. That's wrong. Hence, your transformer, that is why your transformer can change the voltage level at the same frequency, because the turns ratio does not affect the frequency, which implies the phase angle. All right. Okay. So far we've seen on the circuit symbol and the general diagram, you see 2 dots. Okay. Now, we need to look at the dots. We call this the dot convention. The term convention means rules. Okay. some rules regarding the dot. Okay. Now, first we have to understand why do we need a dot? Because the dots are there to help determine the relationship between your primary and secondary side, both voltage and current. Okay. Assume I draw this transformer in a circuit. You know, when you buy, they don't today, but you know, usually when you buy appliances, they would give you like a circuit diagram that you kind of like use it for the serviceman to fix, right? So those are static, right? You see the circuit when your transformer is in a circuit. You have to use that circuit to analyze what is happening to the voltage and current at that given time, and the dot will help. Okay, how does that work? Two rules. One is related to the voltage. The second one is related to the current. Rule number one, convention number one. If primary voltage is positive at the dotted end of the winding, then the secondary voltage would be the same, meaning also positive. Okay, so this is related to the voltage. The second rule, if primary current flows into the dotted end of the winding, then the secondary current will flow out opposite here of the dotted end. Okay, to illustrate what we're doing here, you see here. Here's better. Dot right there, this usually next to the windings. These are the windings. Positive for VP, dot. Then the secondary is the same, dot, positive. For the current, primary goes into the dot, second flows out. So voltage is the same, current's opposite. That's how you memorize it. Okay, now you have to be careful though when we draw the dot. Don't try to kind of like you know, outsmart the circuit. You manipulate it. This is the windings. Usually the dot is right here. Okay, that would be the correct way. But if you don't do that, if you do it like this, if you say the dot's right there, then you say, hey, the current comes in, this is flowing out. But basically, both are the same, okay? So this is not the right way. So here you see the current come in. Or you can say it like this. Current flows out, you see? But you draw the dot pretty far away from the coil, like this one. Then you're going to see it either go into the dot or out of the dot, which is confusing. Okay. So I didn't draw this, you know, close to that, but usually this is how it's drawn. So remember the two rules. Voltage, dot positive, voltage is the same. Current is opposite. So I can have some engineer might be playful. I can have the circuit symbol like this. Dot right there, dot right here. Okay. So when I analyze the circuit, I know, hey, right now here is VP. What happens to the relationship? And we know that if that's positive dot, then positive here, negative there, that's VS. And then current flows in on the primary, then it has to flow out. So this is my IS. So you see how that works. Okay, sometimes, you know, sometimes you can see weird circuit symbol like this. So you got to know how that works. This helps you analyze at a given time what's going to happen to your AC in a regular circuit diagram. Okay, so this is a dot convention. Okay, once we understand that, move on to power relationship. Okay, power in ideal transformer. We talk about that because its ideal input is the same as output. Now we're going to express the input power, which is the primary side. Okay, so it's VP, IP, cosine theta p. So this is an angle between primary phase voltage, primary voltage and primary current phasors. Output voltage, output power, P out. Secondary side usually, so it's VSIS cosine theta S. And of course, theta is an angle between VS phasor and IS phasor. Okay. Now, if you look at this carefully, because turns ratio does not affect theta P or theta S, so that means theta P must equal to theta S, and let that be regular theta, no subscript. This means that primary windings and secondary windings of ideal transformer are have the same power factor. Okay. And if you understand that, we can manipulate this using the voltage ratio. VP over VS equals to A, so you get VP equals to AVS. IP is IS over A. Substitute this IP and VP into the input power. Okay, let me write that down. You have Pin equals to VP, IP, cosine theta P, which equals to theta S, which equals theta. So I'm just going to say theta, no subscript. Okay. I get output power, Vs, Is, cosine of theta. Okay. If it's ideal, both should be the same, and we're going to prove that. Okay. We know the voltage ratio, Vp over Vs equals to A, right? Which equals to Is over Ip. Okay. So if I express this in terms of primary parameters, based on that, I will get Vp equals to AVS and Ip is equal to Is over A. Okay, so far so good. I substitute this Vp and Ip into this equation up top. So I will get Pn equals to AVS times Is over A, cosine of theta. And notice that Ia cancel. So Pn becomes Vs Is cosine theta, which is the output power. So this proves that our ideal applies 100% efficiency. See? So this is the relationship. Okay. Again, once you understand how this works, you can apply the same thing to both apparent power and reactive power. Okay, which would give you S in, VPIP equals to VSIS equals to S out. Similarly, for the reactive power, you get Q in, VPIP sine theta, must equals to VSIS sine theta, which is S out. Okay, so this is power relationship. In ideal cases, it's a simple stuff. Okay. Now, how much time do I have? About 5 minutes. Okay, let me finish this part then. This is an important part. I'll do this and then I'll review it next time too. Okay. Impedance transformation through a transformer. Okay. So what does that mean? If I have a regular circuit like this, let's say I have a circuit like this. Okay. Now, if I want to introduce a transformer in here between these two, it's going to be something like this. Okay. Would this affect the entire circuit? Does it have to change the numbers on this or not? And this is what we call impedance transformation through a transformer. Okay. Now, before we move on, we got to look at the definition first. We know that impedance in nature, Z, in this case, L is for the load. ZL, which is the impedance of the load, is the load voltage, VL, divided by the load current in phasors. Okay, nothing complicated here, just like your Ohm's law. You know, V equals to IR or V to IZ, and then you have Z equals to V over I. Okay. Now, suppose I put a transformer across this load. Okay. If a transformer is placed between the voltage and your ZL, like this. Okay. Now, if I do that, initially I have this. CL. This is VL. IL, right? Now I'm going to say, hey, instead of doing that, I'm going to connect another transformer between the load and the source. The turns ratio of A. So let's say the dot. Okay. If I do that, I got to change some notation. On this side, it's going to be VP, IP, right? Here it's going to be VS, secondary, IS. Okay. Now, if I'm looking at it from the blue line, the blue line in your notes, shown here. The blue, this is what we call refer to the secondary side. You're on the secondary side. Okay. Based on that definition that we use, your impedance ZL will become VS IS. Okay. Nothing changed. I just changed the subscript from L to SS. Okay. We say ZL is impedance referred to the secondary side. We're referring to its own side, secondary. Now, instead, if I want to look at this impedance with the transformer with it, from the point of view of the red arrows, we call this refer to the primary side. Okay, so far so good. If you're on the secondary, you look through that, it's referred to secondary. If you're on the primary, you look the whole thing with the transformer and the load. We call that refer to primary side. Okay. Now, if I treat this whole thing on my right as a single device, my equivalent circuit is going to be like this. Some ZL prime. While this is still VP, IP, where this whole red thing, this is ZL prime. See? So far so good. That's what I have here in the bottom. And based on the same definition, it means that ZL prime has to be the ratio of the voltage divided by the current, VP over IP. So far so good. Then what do? I manipulate VP in terms of VS, which is AVS. At the same time, I also manipulate IP in terms of IS, which is IS over A. If you do this, A would not cancel. It turns out that the whole thing is going to become A squared VS over IS. Okay, make sure you understand what we're doing here. Okay, and if you look carefully, your ratio of VS over IS is actually ZL. Put that in. Okay, you're going to get A squared ZL. Okay, and match that, it becomes ZL prime is A squared ZL. This means what? This means that my impedance referred to the primary, I'm just going to call it primary for short, is equal to A squared times the refer to the secondary. See, primary is A squared, secondary, where A is the ratio of the primary turns divided by the secondary turns. Okay. So the turns ratio would have an effect on the regular impedance. See, if it's 1-to-1, there's no effect, but if there are other numbers, that would change. Okay. I should stop. I'll come back and give you a numerical example later. But this is, you have to remember this concept. This is very important concept in the transformer chapter. If you don't understand this, then the rest of the chapter is going to be gone. You're not going to understand anything. You need to understand this concept. So your job is to go back and read what we're doing here, the transformation, and remember the equation and remember the relationship. Okay, I will stop here for today. Okay, lots of explanation, so it's going to be like pretty sleepy class, but Okay, go back and read this, understand what we're doing here, especially the last topic that we discussed. Any question?
No, sir.
All right, and if there's nothing else, again, stay healthy and stay safe. I'll see you next week. All right.
Thank you for today, Ajahn. See you next.
Thank you, sir.
Bye.
Thank you, sir.
Thank you, Ajahn.